Hey, everybody.
Hello.
All right, let me share my screen and we'll get started. Oop, wrong class. Let's see. Let's just start a new document here and do some screen juggling on my computer. All right. And now you don't see it anymore. Okay, cool. What do we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We got 10. Hey, that's pretty good. I think there's only 12 total. So it's all but 2. It's enough to start. Let's get started. I hope you all got my email with everything we've done in the homework assignment. Couldn't find any web work problems on the stuff we talked about last time. So I recommended some homework problems out of the book. And I actually want to go through in detail one of those problems, which was problem 18. So before we get started, are there questions on any of the other ones besides 18? Going once, going twice? All right, let's go through 18. And then also I recommended 19. The instructions for 19 are pretty minimal, but for 19, they really just want you to mimic where it'll go through in 18. So we'll go through everything in detail in 18, and then you try 19 yourselves and try that on your own. Okay? All right. So problem 18 here. Uh-oh, that's my son playing drums in the background. Let me tell him to be quiet. 1 minute. Okay, I'm back. All right, sorry. All right, problem 18. We've got this system. Rearrange my work surface here. Here we go. We've got this system, the x dt equals y, and dy dt equals x squared minus a. And then they say, verify that this is a Hamiltonian system, and they give you the Hamiltonian function. So the Hamiltonian function, you should, at this point, you really should be able to come up with that Hamiltonian function yourself. But since they give it to us, let's not worry about it. So the function they're telling us is h of xy equals y squared over 2 minus x squared over 3 plus ax. Now the thing you have to worry about when you have a Hamiltonian function is that the partial with respect to of h with respect to y is either dx dt or negative dx dt, and the partial of h with respect to x is either dy dt or negative dy dt, and they should be opposite. So really the condition just goes back to the very beginning of the book. We want to check that 0 is the partial of h with respect to t as long as we're traveling along solution curves of the system. So just a reminder of what we did last time. If we use the chain rule, that means that that is the partial of h with respect to x times dx dt plus the partial of h with respect to y times dy dt. That's just the second equality there is just the chain rule, and the first equality is what it means to be Hamiltonian. Okay? And now we're going to use the function they give us to compute these two partials, and then we're going to use the original system and plug them in here, and then we're going to just check, does that equal 0? That's how you check if it's Hamiltonian, okay? So let's just go through it. So partial of h with respect to x, let's do that first. That's this piece of the puzzle. So just look at h and just yell it out or I'll just do it because I trust you can all take the partial with respect to x of a function. So we differentiate y squared over 2 with respect to x, we get 0. We differentiate x squared over 3 with respect to x, we get minus 2x over 3. And ax gives us a. Okay, so that's this bit of it. We also need the partial of h with respect to y. That's just 2y over 2, which is just y. Okay, and that's this bit of it. And then we just put it all together and make sure we get 0, right? So we want, again, we want partial of h with respect to x, dx dt, plus partial of h with respect to y, dy dt. So let's just write that out. Partial of h with respect to x, we said was minus 2x over 3 plus a, times dx dt, which is way up here at the top, that's just y, plus partial of h with respect to y, that's here, is y, times dy dt, and dy dt is back here at the top, that's x squared minus a. And now we multiply this out and hope we get 0, and I'm feeling like I did something wrong. Ah, I did do something wrong. The Hamiltonian function from the book, I didn't copy it down right. It's y squared over 2 minus x cubed over 3. So all that changes is down here, the partial with respect to x is 3x squared over 3 plus a, which is just minus x squared plus a, which is down here. Okay, better. And now that all certainly looks like it's 0, right? Because we have y's in both terms, and minus x squared plus a and x squared minus a, which one is the negative of the other there. It certainly looks like everything's going to cancel and give us 0. I'm just talking here and staring at my iPad. I'm not even looking up at my screen, and I'm just writing. So please, 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 please turn on your mic and stop me, slow me down, whatever you need to do. Okay? All I did was I did this computation and made sure we got 0. I'm just going through the problem in the book, and we'll get to the more interesting parts of this problem and the reasons why I signed it in a minute. One thing to notice about this problem just from the very beginning is there's an a in it, okay? Now that a is, you're thinking of that as a constant. It's not changing as time changes, and it doesn't depend on x, and it doesn't depend on y. It's a parameter. And the system will behave differently depending on that value of a. And that's really what this problem is about, is understanding the different types of behaviors of the system depending on the different values of a. Right? So at this point, we've confirmed that it's a Hamiltonian system. And we want to go through and check the equilibrium points. And that's the next part of the problem. It says, show the system is equilibrium points at plus or minus square root of a, comma 0 of a is greater than or equal, and no equilibrium points of a is less than 0. So again, we're going to set, let me change colors here. We're going to set this equal to 0 and this equal to 0. So this just gives us y equals 0. And this gives us x squared equals a, which means x equals plus or minus square root of a. But we can only take that square root. We're only looking, we're looking in the real plane. X and y are real numbers depending on t, which means in the real plane, in the real xy plane, this only has a value when a is greater than or equal to 0. So if we put all this information together, we do get plus or minus root a comma 0, but only when a is greater than or equal to 0. And we get no equilibrium points if a is less than 0. That's exactly what they ask you to show. Good there? We have two equilibrium points, a plus or minus root A, and as A gets closer and closer to zero, think about, so this is, it's kind of interesting. I mean, let's think about what's happening here for different values of A. So we've got equilibrium points where X is plus or minus square root of A. So at positive square root of A and negative square root of A. And as A gets, think about now, A getting smaller and smaller and smaller. As A gets closer and closer to zero, those two equilibrium points are going to get closer and closer together. Eventually, they're going to converge right there at the origin. And then when A goes negative, suddenly they disappear. And we have a system with no equilibrium points at all. And that's what we typically call a bifurcation value. A bifurcation is when the nature of the system somehow changes. So when A is positive, we have two equilibrium points. When A is negative, we have no equilibrium points. So that behavior of that system qualitatively changed when A hit zero, which is why A equals zero is called a bifurcation value. Somebody's got their mic on. Maybe it's me. Do I have my mic on? Oh. Okay. All right. Let's keep going now. They say linearize the system at each equilibrium point and determine the behavior of the solutions near the equilibrium points. So we only have equilibrium points if A is greater than or equal to zero. So we'll just go ahead and assume that now that A is greater than or equal to zero, and think about what happens. What does the system look like around each of those points? So again, the system is dx dt equals y, dy dt equals x squared minus a. And we got to compute the Jacobian. So we need the derivative of the first function with respect to x, the first function with respect to y, the second function with respect to x, and the second function with respect to y. That to me looks like the Jacobian matrix. We are going to evaluate that matrix at where at the point plus or minus square root of a comma 0. So x is just plus or minus root a. So that's now the matrix is 0, 1, plus or minus 2 root a 0. Characteristic polynomial is going to be minus, if I put a minus lambda where the zeros are and take the determinant, we get lambda squared minus plus or minus. So when you subtract plus or minus, you get minus or plus 2 root a equals 0. So lambda squared equals plus or minus 2 root a. So lambda equals, oh boy, the square root of plus or minus 2 root a. So let's think about that. So we get two roots here. One of those is the square root of 2 root a, and the other is the square root of negative 2 root a. So the negative one, what kind of singularity is that? What kind of equilibrium point is that? Anybody want to venture a guess there? Maybe put it in the chat window. I'll pull up my chat window.
Center for the negative one?
Yeah, the negative one's a center. Good. Oh, and Ezra, you told me I think it's supposed to be x cubed over 3. I didn't have my chat window up, so I never got that. Thank you. You had pointed that out probably long before I caught it. Thank you, Ezra. Right, this is going to be a center. And the other one is we've got a positive eigenvalue. Well, sorry. For each of those values, when lambda, when we're at the equilibrium point, positive 2 root a, then at this point, so sorry, let's back up a minute. There's 2 equilibrium points, right? So from the very beginning, there was, if we're at the equilibrium point, positive root a comma 0, then at this point in the derivation, we're getting lambda squared equals 2 root a. So lambda is plus or minus square root of 2 root a. If we're at the other equilibrium point, minus root a, then at this point in the derivation, we've got lambda squared equals minus 2 root a, so lambda equals plus or minus the square root of minus 2 root a, and that is a center. And this one, the one on the left, root a comma 0, we've got both a positive and a negative real root, so that's a saddle. Okay, so we've got, remember with the Hamiltonian function, all we can have are saddles and centers. So what we're getting here is totally reasonable. So what we're seeing in the picture is a center tangency around minus a and some sort of saddle tangency around root a. So I would guess it looks something like this. We saw a picture kind of similar to this last time, where it probably goes off and does something like this. The thing to think about now is that a is a variable parameter. So as a gets closer and closer and closer together, as a gets closer and closer to 0, those 2 points get closer and closer and closer together. And you should think about what happens when they might collide. When they collide, you should kind of think about a cartoon, a sequence of pictures here. We've got a point and these circles, and these x's, and these, and that. And now as those 2 points get closer and closer together, you got to think about how that changes the picture. Now we get those 2 points really close together, and we get things that and then eventually, when a goes past 0 into the negative range, decreasing a, we're just going to get no equilibrium points at all. So things will look just kind of like this. I hope you can see I've tried to draw kind of a cartoon here of what would happen as we vary those equilibrium points as they get closer and closer and closer together and then eventually cancel. And then we have no equilibrium points. So this is kind of an interesting system because in the end, when a is negative, we have almost no tools. We can look at null clines. I don't think the null clines are going to give us a lot of information. When a is negative, we have very little. We have no information from equilibrium points because there aren't any. But I still drew something like a sketch, something like a picture of the situation when a is negative, because we're thinking of it as the limit of situations where a is positive but getting smaller and smaller and smaller. And for all those positive values of a, we know what the picture looks like because we know we have a center tangency and a saddle tangency. Center equilibrium point and saddle equilibrium point. And you just got to think carefully about what the pictures look like when those two things collide. What do you think? Good? All right. I mean, one of the things we can do is we can go into a 3D graphing program. I mean, we're going to do this a lot. I'm going to work out another example where you'll see the same thing. And we can look at that Hamiltonian function and sketch the level curves for different values of a. And this is the whole point. It's the level curves of the Hamiltonian function. should be consistent with the pictures that we're getting. So let's do that. Let me now share my desktop where I have a graphing program all set up. You all seeing that? Yeah. Okay, so now I'm going to type in the Hamiltonian function, which was y squared over 2 y squared, no, over 2 minus x cubed over 3 minus x cubed over 3 plus, now it was, the original system was plus ax. So I'm going to do plus 1 times x, and then we'll make that 1 smaller and smaller and smaller. So here's that system when a is 1. And let me just change the coloring here to make it clearer what's going on. Let's do uniform colors, and let's show those contours so you can really see it. And here, I think you can really see that saddle tangency over here on the right side, that center tangency there on the left side, and you're seeing what's happening there. Okay. I can also do this in 2 dimensions. It's near a 2-dimensional picture, kind of side by side with a 3-dimensional picture. So let's take this function and do it 2-dimensionally. And I don't want colors, I want contours. Yeah, and you can kind of see it now. Zoom in a little bit. Yeah, there it is. There's a good picture. Okay, so maybe zoom in a little bit more. Not too much. All right, so there are the contours of this 3-dimensional function, so you can see the surface there. And that's all when a equals 1. So now let's see what happens to both these pictures when a equals 1/2. So instead of that 1, I'm going to change that to 0.5. And oh, now my coloring's off again. You can see what happened was this saddle point decreased and the minima increased, and eventually those two are going to level off to the same level. In the 2-dimensional picture here, let's see, let's again do 0.5. The colorings are probably going to go way off again, yeah. There we go. And let's stick with this picture. Let's go down to all the way down to 0, just so we can see what happens. That's what happens when we get 0. We can look at the 3-dimensional picture when a is 0. I'll give you some kind of feel. There's the 3-dimensional picture when a equals 0. This profile of this surface, the edge of the surface looks a lot like the graph of y equals x cubed. In fact, that's exactly what it is. It is the graph of y equals x cubed, because that's the intersection with the xz plane, where y equals 0. And if you look at the equation, it's actually x cubed over 3, minus x cubed over 3 is the equation we're seeing there. Right? So we do have a critical point right there, place where there's a horizontal tangent. But if we tilt that horizontal tangent at all, one way, we don't create a critical point. And if we tilt it the other way, we create 2 critical points, a saddle and a center. So there's a lot of 3-dimensional stuff going on here that it really helps to understand when you're trying to reconcile all these pictures. Let's do one more quick example here. What happens when x is negative, when a is negative? Let's go all the way to -1. That changes the 3-dimensional picture by continuing to tilt that. Now there's no critical points at all, right? And we can look at the level curves. And that's annoying. Here are the level curves now. Right, so there's no more equilibrium points anymore. They kind of disappeared. If I zoom out, then you can see what they look like from a distance. Zoom in. They still kind of look like they did before. When I zoom all the way out, you still get this big bulge going around the origin for big values. Right, so there's a lot of similar qualitatively similar things, but right around the origin, things are different because there's no equilibrium points that are right around the origin. I hope I'm trying to help build your intuition here and also convince you that Hamiltonian functions are super useful, because rather than plotting the vector fields in the system, we could just look at the graph of this surface and think about how the surface changes as we change A. And that really tells us everything about the system. And we don't need to do all that equilibrium point analysis. We just need to look at the contours of the surface and think about how those contours change as the surface changes when we change the value of A. Does that help shed light on this at all? I mean, maybe, maybe not. Robert gave me a thumbs up. All right, thanks, Robert.
You're welcome.
All right, let's go ahead and jump into another example. Let's get rid of these. I want to do another example that's in the book that we didn't do last time. And that's going to lead us into the next chapter. So the next example is straight out of it really leads us in. It forms a nice segue between the chapter we're doing now and the next chapter. So let me go back to my iPad screen. Back to my iPad screen. All right, now I got to juggle windows again. Every time I go to my iPad screen, I got the computer. I'm working on 2 screens. And my computer, by default, every time I share my iPad screen, wants to put my iPad screen on the screen I'm looking at, and you all on the other screen. But that's annoying because I'm always looking at you all, and I want to be looking where the camera is. Whatever. I have to, every time I share screens, I have to rejuggle all my screens, all my windows. All right, let's go to the next example. So the next example is one that I actually, now looking back on things, don't think this is in the book earlier in the chapter, but if you watch the recorded lecture I gave last week when I was in Portland, I went through the next example in pretty good detail. But at the time, we didn't have the language of Hamiltonian functions. And so now we're going to add to that discussion the fact that was a Hamiltonian system that we were looking at. So the system is the pendulum. So again, just to remind you, we've got just a simple frictionless pendulum here. Okay, and we're modeling this. There's a force of gravity pulling us down, and there's an angle up here, theta, and there's a mass. It's got some mass, and the pendulum has some length L, and all of these are parameters that ended up being part of the system. If you watched the recorded lecture I gave last week, I forget which day it was. It was Monday or Wednesday. I think it was Wednesday. I tried to go through Newton's laws and the physics and the trigonometry, and we get some sine thetas popping up in there. I'm not going to go through all of that again. It's also in the book. So if you missed that lecture, I encourage you to either rewatch that video or just read the book. It's in this section 5.3 on Hamiltonian systems that we've been looking at. I'm just going to jump down to the answer, and I'll remind you what the picture looks like. The system we ended up with was d theta dt. First of all, we ended up with a second order differential equation, a single equation that was second order, but then there was this extra step to introduce a variable like we've done in the past many, many times. We introduced this v variable, which is the rate of change of theta, to make it a first order system. So we changed this from a second order equation to a first order system. And what I'm writing out now is that system. V is this new variable we introduced to break it up. And then dv dt, which is really the second derivative of theta, is minus g sine theta. And this was assuming there was no friction. Probably hearing my son singing in the background. Just ignore that. I'll try to talk over him. Okay, so that's the system we're dealing with. And I'm just going to pretend g equals 1. And, whatever, you can always pick units so g equals 1. They're not traditional units that physicists use, but we're mathematicians, so we can pick whatever units we want. So if we pick g equals 1, then our system is just dv dt equals minus sine theta. Now, the other difference, if you learn this in a physics class, if you went to a physics class, is v here is the rate of change of theta. So physicists don't call that velocity, they call that angular velocity. It's the rate of change of the angle. And they're pretty consistent. Physicists are much more careful than mathematicians. They usually use v for velocity, which is rate of change of position. And they use a Greek letter to talk about rate of change of angle, which makes sense because theta is what we use for angle. So they'll use like a Greek letter omega for angular velocity. I want to be consistent with what's in your book right now. And I don't remember what letters I used when I gave this lecture last week. So we're just going to go with the letters that are in the book, where they used v for the angular velocity, which is the rate of change of theta. And that's what that first equation is. V is the rate of change of theta. All right, now given all of this, I went through the linearization last week. Again, I'm not going to redo all of that, but I'll try to sketch the picture that we came up with. We got an infinite number of equilibrium points on the, let's see, this is the theta v axis. There was one right there at the center, and then one at pi, 2 pi, etc., all multiples of pi. And the nature of those equilibrium points changed. At the even multiples of pi, we had center tangencies. And at the odd multiples of pi, we have saddles. And then I just claim that you could kind of fill in the picture like this. It's a little bit of a brash claim, and a lot of that just comes from experience. And then things look kind of like this. And I think we even did a little bit of work to decide what direction things were moving in. And let's see, they're moving this way. Etc. Okay, so again, watch the lecture from last time or read the book to remind yourself where all that's coming from. We did basically just a full equilibrium point analysis of all the equilibrium points and pieced together this picture from that equilibrium point analysis. And what I reminded you or tried to convince you of during that lecture was that this is totally reasonable, and it should completely agree with your intuition about pendulums. About if you have a hanging pendulum, then if I just knock it a little bit, if there's no friction, it's just going to go back and forth. So the angle increases while the angular velocity decreases, it slows down. Then you start moving the other way, the angular velocity picks up speed, where the angle now is 0, and then the angle goes negative, and the angle of the velocity goes to 0. And it's just going to keep oscillating back and forth and back and forth. And that represents exactly one of these circular curves. Think about what's happening on one of these circular curves. On one of these circular curves here. First, the angle is getting bigger. On the circular, on the circular curve, as you go around that circular curve, the angles, which is what's happening on the horizontal axis, is just going from positive to negative to positive to negative. And what's happening on the vertical axis, the angular velocity is getting bigger and smaller and bigger and smaller. And that's exactly what's happening as the pendulum is oscillating back and forth. And when the angle is smallest, which means we're right there on the vertical axis, that's when the angular velocity is biggest. That's where we're up here at this point at top. And over here, the angle is biggest, right? We're all the way at our extreme, but the angular velocity is smallest because it's slowed down to a stop before it goes the other direction. And then the angular velocity goes negative and the angle is small, and then the same thing over here. Now we're back in the other position on the other side. Right, so this circular trajectory in the theta v phase plane is totally reasonable, okay, if the angular velocity is relatively small. But if I give this pendulum a really big kick, if I really whack this hard, which I don't want to do because it'll go flying, it's going to go around and slow down a little bit. But then if I give it enough of an initial kick, it'll keep going all the way around, and all the way around, and all the way around. Okay. And if there's no friction, that'll just keep happening forever. So it does slow down and speed up and slow down and speed up. But that angle keeps getting bigger and bigger and bigger. Right? 1 revolution gives me 2 pi, 2 revolutions gives me 4 pi, 3 revolutions gives me 6 pi, right? So the angle is getting bigger and bigger and bigger and bigger. And that's exactly what's happening on this upper curve here. You can see the height, which is the v coordinate, is getting bigger and smaller, right? It's speeding up, slowing down, speeding up, slowing down. But the angle itself keeps increasing, bigger and bigger and bigger as it goes around, right? If I instead kicked it the other way, it's going to go around and around and around, and the angle is going to keep decreasing, decreasing, decreasing. And that's exactly what's happening down here at the bottom. Is the angular velocity is again oscillating while the angle gets more and more and more negative. Right, so those are the 3 kinds of behavior, where it's either going to spin one way, spin the other way, or it's just going to sit there and oscillate. Right, and we're seeing all 3 of those as different kinds of solution curves in this picture, these circles and these curves. Okay, all right. Now, again, I'm just reviewing all of that, just a review of what I hopefully said in the recorded lecture from last week. The new bit of information is that this is a frictionless system. And in a frictionless system, any physicist will tell you that there must be constant energy in that system. That's really kind of what it means to not have friction. There's no energy being dissipated. So there must be some quantity called energy that the physicists label that stays constant no matter what's going on, okay? And that's exactly our clue that this is a Hamiltonian system. So without knowing anything else, we should be able to find a Hamiltonian function for this system. So again, let me copy that system down at the bottom of the page there without the g, because we're assuming g is 1. So we have d theta dt equals v, and dv dt equals minus sine theta. So if this is a Hamiltonian system, it means there's some Hamiltonian function where this is the partial of that function with respect to v, the negative partial of that function with respect to v. And this is the partial with respect to theta. Okay? So again, now I'm doing this partly to review from last time because I think I lost some people last time. So let's just look at each of those clues independently. We have 2 clues to what h is. One clue is that the partial of h with respect to v is negative v, right? I've just brought the negative sign to the other side. The other clue is that the partial of h with respect to theta is minus sine theta, right? So we're trying to figure out what this mystery function h is, and we have 2 clues about that mystery function, which are the 2 partials. Right? Now, knowing that the partial of h with respect to v is minus v, now we can integrate to say, give us a little bit of information about what h was. If we integrate with respect to v, what happens if we integrate v with respect to v?
Doesn't it become like negative 1/2v squared plus c?
Okay, yes, good. Plus c, thank you, Amber. Now that c, we just did an integral with respect to v. That plus c means we're picking up anything that doesn't change when v changes. So that thing we're picking up, that plus c, could be a function of theta. Any function of theta is a constant as far as v is concerned, right? So it's this plus some function of theta that we don't know yet. That would be consistent with this information. Think about, if you want to think about why that is, just think about differentiating this with respect to v, and you'll see that function of theta just disappears. Okay. All right, now that's our first clue. Our second clue is that h d theta is minus sine theta, so that tells us a little more information about what h is. H has to be, well, we can integrate both sides with respect to theta. Integral of minus sine theta with respect to theta is what?
Cosine theta.
Just cosine theta, good. Okay, plus some function of v, right? Because a function of v is a constant as far as theta is concerned. All right, now these are two clues as to what h is, but h is just a single function. So we have to find a single function for h. It's a function of theta and v, so that it's simultaneously minus 1/2 v squared plus some function of theta, but it's also cos theta plus some function of v. So what is h?
I got negative 1 over 2 v squared plus cosine theta.
Correct. Negative 1 over 2 v squared plus cosine theta. Just a word of warning, if you follow this in the book, instead of putting the negative sign here, they put the negative sign down there. And you can put it in either place you want. Either calculation will give you a Hamiltonian function. Okay, either way. So just a word of warning if you have the book open and you're following along in the book, or you want to see what the book does later. So they got positive 1/2 v squared minus cos theta. Both are Hamiltonian functions. All right. So now now that we have that Hamiltonian function, we can look at its level curves and make sure the level curves are consistent with this picture. So we actually didn't have to do any of that equilibrium point analysis last week. All we had to really do was get this Hamiltonian function, which is actually a whole lot less work than all that equilibrium point analysis we did. And then we'll know what the picture is. Okay. So again, I will flip back to my graphing program, and I will share desktop one. There we go. Hopefully you can all see that. And let's see, when I typed this in earlier today, I typed it in with the book's answers, but let's be consistent. So we just got minus 1/2. Unfortunately, I can't do v's and thetas. I can only do x's and y's, but it's the same thing. So x in this program is the theta we got, and y in this program is the v we got. But the answer looks like that, right? Function there. It looks from the side, it looks kind of like a sinusoid, and from the other side, it looks like a parabola, which makes sense because from one side, we're just seeing that minus 1/2 y squared, downward pointing parabola. From the other side, we're just seeing that cos x. Right? And let's see what the level curves look like. So let's make this a uniform color and look at some contours. And if we do that, we're now seeing nice level curves, which are exactly like the picture we were getting before. Amber, you have a raised hand. What's up, Amber?
I was just curious if you could explain, in this example, like as you're explaining, how the 2D picture gets the 3D picture again, like level curve bit.
Right, the level curve. So the whole point of Hamiltonian functions is you find a Hamiltonian function by solving for some function whose derivative along the level curves is 0. Now, another way to say that is if the derivative of a function is 0, it means that that function is a constant, it's horizontal. So along the level curves, the value of that function h along those trajectories, the value of that function h isn't changing because we set it up so dh dt is 0. And if dh dt is 0, we're staying at the same level. So it's saying solutions of the system, trajectories of the system, are places where h is constant, which means we're at these levels. I don't know if that helps at all. It's a little bit, the logic there is a little bit complicated. But,
Yeah, it does. Thank you.
yeah. Sometimes it's a little hard to see these three-dimensional pictures, so let's do the same thing again in 2 dimensions. Again, let me rewrite. This was minus for us, and this was a plus. And let's take a look at that. And again, I can color it. Let's take off the coloring and just look at contours.
Professor,
Yeah.
if you were to add a third element like plus sine x, would that add a different dimension to
No, it would still be three-dimensional. You mean if we had an x, a y, and a z?
Yeah.
Like if we had dx,
yes. Plus sine z or something, yeah.
Yeah. Great question, yes. So, and in fact, that's exactly the last section of chapter 5. We're still in 5.3, Hamiltonian systems. 5.4 is called dissipative systems. We'll get to that. Today we'll start that. And then 5.5 is on three-dimensional systems. And we're going to do exactly that, yeah. And there are three-dimensional Hamiltonian systems whose trajectories lie on level surfaces of a four-dimensional graph. We're not going to do that so much, but we will look at equilibrium point analysis for three-dimensional systems.
Okay,
yeah.
Got it.
Yeah. Just for comparison, by the way, I have this all set up to look at the vector field from the original system, and it's there, and you can see it. It agrees really well with those level curves. It should be right on the nose, exactly the same. The level, so the curves you're seeing in this graph are the level sets of the Hamiltonian function, and the arrows you're seeing are the solutions from the original differential equation. You can see that they really agree quite nicely. Kind of cool. I think it's cool. I think it's nice to see all these things together. All right, good. We move on. Thumbs up. Questions about this? You good? Okay. All right. Let me go back to my iPad screen now and have to rearrange my windows again. What do we got? It's 11:50. Okay, so we've got 25 minutes. So we are going to start the next chapter here. And the next chapter starts with this exact same pendulum example, but they throw in one more additional detail, which is friction. So in the next chapter, they say, okay, well, let's see what happens when we get a little more realistic and we look at what happens with friction. And I'm not going to go through all the physics, partly because I'm not a physicist and I always kind of flood things. I always get a sign wrong in physics, whatever. I'm a mathematician. That's every mathematician's excuse for being bad at physics. All right. So again, we've got the same. I'm just literally going to copy down what's in the book. So we've got the same pendulum, all the same stuff. It's got some force of gravity. It's got some mass. The pendulum has some length. We're still going to call this angle from the horizontal theta. But there's some other stuff going on now, which is friction. Now, friction acts always opposite to the angular velocity. So the faster the pendulum is moving, the more friction there is. When the pendulum's moving very, very slow, there's very little friction. So the differential equation you end up with, it's a second order differential equation. Oops. Is this. Okay, and it's this term that's new. That's the friction term. B is what the force of friction. B is how much friction there is in this system. So this extra parameter now we have to introduce. And that parameter is a coefficient of d theta dt, which tells us that the more the angular velocity, the more d theta dt, the more friction there will be. And it's all proportional to the angular velocity. Okay, so if you do the physics, you do Newton's laws, you do the geometry, trigonometry, you get down to that system. And now again, we can linearize that system in the same way. Sorry, not linearize. We can convert that second order equation to a first order system by setting d theta dt equal to a new variable, which again we'll just continue to call v. And if we do that, then dv dt is takes the place of d squared theta dt squared up at the top, and it ends up with minus b over m v minus g over L sine theta. And now I'm going to exercise my right as a mathematician to pick whatever units I want. Physicists don't have that right, but I love being a mathematician, so I don't have to worry so much about units. I'm going to pick all my units and all my constants, so all those coefficients are just 1. So I'm going to rewrite this again. So b over m is just 1, and g over L is just 1. And so now we're looking at the system d theta dt equals v, and dv dt equals minus v minus sine theta. Okay? So that's almost exactly the system we were working with before. The only thing that's new is this minus v term. So minus v is just the friction term. That's just exactly the thing we need to introduce to compensate for some friction. And again, you know, in the real world, there'd be some constants in front of that v, so you can adjust the amount of friction there is. Okay. Let's do the equilibrium point analysis. Shouldn't take us too long. See what it is, then we can graph it, see what that is. It's not Hamiltonian anymore. It's friction. There's friction. What friction does is it converts energy to heat. So the amount of energy in the system is not staying constant. Some of it is turning into heat and leaving the world. Okay? Physicists, if you take a class in thermodynamics that I haven't done, you can look at the amount of heat plus energy in the system, and that's constant. I don't know anything about thermodynamics. I never had a thermodynamics class. So but we'll be able to tell right away that this can't be a Hamiltonian system once we do the equilibrium point analysis. Let's just do it. So first we have to find the equilibrium points. So we set this equal to 0. Well, that's easy. So v is always 0. Then we set this equal to 0, setting that second equation equal to 0, and knowing at the same time that v equals 0 tells us again, these two equations together tell us that sine theta equals 0, which means theta is just a multiple of pi. So it's the exact same equilibrium points we get before. On the theta axis, we see multiples of pi, and on the v axis, we see 0. The exact same equilibrium points we got before. 0, pi, 2 pi, 3 pi, negative 2 pi, etc. Okay, all the same. All right, let's now do the, get rid of this. Let's now do the I'm blanking. Let's do the linearization around each equilibrium point. So to do that, we've got to get the Jacobian matrix. Partial of the first function, which we set to theta, is 0. First function with respect to v is 1. Second function with respect to theta is minus cos theta. And the partial of the second function with respect to v is minus 1. And again, that minus 1 is new. It wasn't there the last time we did this. Okay. Now there's two possibilities. Either theta is an even multiple of pi, or theta is an odd multiple of pi. Those are the two possibilities for the different matrix. When theta is an even multiple of pi, cosine theta is 1, right? So we get 0, 1, minus 1, and minus 1. When theta is an odd multiple of pi, cosine theta is negative. So we get 0, 1, negative, negative 1 is positive 1, and negative 1. Good. All right, let's keep going. So we want to subtract lambda, get the characteristic polynomial, and we get lambda times 1 plus lambda minus negative 1 equals 0, lambda plus lambda squared plus 1 equals 0. So that doesn't factor. Lambda equals minus b plus or minus the square root of b squared minus 4ac all over 2a, which is minus 1/2 plus or minus 1/2 times the square root of negative 3. What is that? What kind of equilibrium points are those? Got a complex number with negative real part.
Spiral sink.
Spiral sink. Okay. Okay, let's do the other one. Subtract lambda, subtract lambda. That gives us lambda times 1 plus lambda minus 1 equals 0. Lambda squared plus lambda minus 1 equals 0. Going kind of fast here. Lambda equals minus b plus or minus the square root of b squared minus 4ac gives us plus 4 all over 2a, which is minus 1 plus or minus root 5 over 2. Root 5 is bigger than 1. So when we add root 5 to negative 1, we get a number that's positive. And when we subtract root 5 from negative 1, we get a number that's negative. So we have a positive and a negative real number. So hopefully you all have that drilled into your head at this point, that is a saddle. And so at the odd multiples of pi, we have saddles. And at the even multiples of pi, we have spiral sinks. So let's think about this picture. Just like before, at the odd multiples of pi, we have saddles. This is exactly what we had before. But before we had centers at the even multiples of pi, so there were circles surrounding the other dots. Now there are spiral sinks. I don't know if they go clockwise or counterclockwise. I'm going to draw them all as clockwise. And so now it looks to me like probably things are just spiraling in somehow, like this, and maybe they go like this. Okay, now again, this is actually a very reasonable picture for a pendulum. Let me see if I can describe what's going on here. Actually, probably what's happening is we get, let's look at a curve like, here's, I'll draw one more trajectory here. This one here. Okay, so that last one I just drew, we'll do it in red so we can emphasize what it is. So it's this one right here. I'll try to describe what's going on there. Okay, so what that is it's a pendulum, okay, that's been given enough angular velocity that it's spinning. And it is speeding, again, just like before, it's speeding up and slowing down and speeding up and slowing down. It's spinning in the negative direction, so theta keeps getting more and more and more negative. It's speeding up and slowing down, but now there's friction. So so even though it's got enough energy to make it all the way over the hump, every time it goes around, it's losing some speed to friction. And at some point, it'll get slow enough that it won't quite make it over the hump, and it'll stop right up there, and then it'll start going the other way. And theta will go negative, and then theta will go positive, and then theta will go negative, and that's going to slow down and slow down and slow down, and it'll oscillate, and the value of theta goes positive, negative, positive, negative, positive, negative, until it just, wiggles down to zero. So everybody see that? That's what's happening with that red curve. And that red curve, it's spinning around and around and around, but it's losing energy each time until it gets to the point where it can't quite make it over the hump. And then theta, the value of theta is just going to oscillate back and forth, back and forth, back and forth. Well, I think if you really think about this picture and think about a pendulum that has friction, this picture makes total sense, at least to me. Should totally agree with your intuition, what this picture is saying. And on the opposite side also, if we have something that's spinning around in a positive direction, spinning around, but losing speed, and then eventually it'll spiral in. When it can't make it over that hump, it just starts oscillating in the positive direction. Right, so that's a typical kind of solution for this. Okay. Let's look now at, let me share my screen before we go a little any further. Okay. Again, you should all be seeing the work we did before. And now I'm just going to change one little thing here. I'm going to keep the level curves the same. So again, the level curves you're seeing are the level curves of the original Hamiltonian function when there was no friction. This isn't Hamiltonian anymore. I'm going to change that second coordinate function, and I'm going to put that minus y, because that's the new system we're dealing with. And now let's see what happens to those arrows. Okay. Now you see where the saddles are, they still look like saddles. If you look in the left and right side of that picture where the saddles were, it still looks like saddles, roughly the same saddles. Okay, if you think about the arrows are pointing away from that equilibrium point in two directions and toward that equilibrium point in the other two directions. You all see my mouse pointer, right? Yeah, good, okay. All right, in the center, you're seeing things spiraling in clockwise. And hey, I got my direction right. I had a 50-50 chance of getting the direction right in the picture I drew. And it looks like I got it right. So things are spiraling around clockwise until they get to the middle. You can really see that in the vector field. Okay. All right, now the reason to superimpose both these is it kind of gives us a clue what's going on. And if you think about the Hamiltonian function, it also gives us a clue what's going on. So the Hamiltonian function we came up with before was minus 1/2 v squared plus cos theta. Let's take a look at that. I'm going to go back to sharing my iPad screen. Okay. Juggle my windows. There we are. All right. Let's take a look now again. Again, I'm just going to copy down one more time. The system I'm dealing with is d theta dt is v, and dv dt is minus v minus sine theta. Without that minus v, we had a Hamiltonian function. And the Hamiltonian function we came up with was 1/2 v squared, minus 1/2 v squared or 1/2 v squared. Now I've gone back and forth so many times I've forgotten. What did I have before? We had minus 1/2 v squared plus cos theta. All right. Now, previously it was Hamiltonian. So that meant dh dt was 0. Sorry, d's. The derivative of h with respect to t was 0 along trajectories. And when I say along trajectories, I mean along places where we know what d theta dt is and dv dt is. They're given by this equation. Let's use the same Hamiltonian function h and do the computation. Figure out what dh dt is. It's not going to be 0 anymore, but we'll see what it is, and that's actually going to give us some information about the original system. So we're going to use the same Hamiltonian function, but we're going to use it with that minus v term and see what is dh dt now, right? So let's just do the computation. So we want dh dt, again, this is now the multivariable calculus chain rule. That's the partial of h with respect to theta times d theta dt plus the partial of h with respect to v times dv dt. Okay, all right. So partial of h with respect to theta. We want the partial of h with respect to theta. Well, the first term disappears. Derivative of cosine is minus sine. So we get minus sine theta. That's that first partial. Times d theta dt. That's up here. There's d theta dt. That's just v. Plus partial of h with respect to v. Well, the derivative of minus 1/2 v squared with respect to v is negative v times dv dt, which is minus 1. Oops. No, right. Sorry. I got to go back up top. dv dt, here's dv dt. It's minus v minus sine theta. Okay, all right, let's keep going. So that's minus v sine theta plus v squared plus v sine theta. And the v sine theta terms disappear, and we just get v squared. All right. We got v squared. V squared is always positive. And that's the key observation here, is that the derivative of h with respect to time is always positive along solution curves. Okay? Now, remember h, if you think about h, it's this three-dimensional function. So I'm walking along solution curves of my system, and my derivative of h, of my height function, is always positive. So what does that tell us geometrically? If your derivative is positive as you walk, if your derivative of height is positive, think about you're walking along a trail on a mountain, okay? This mountain trail is your solution curve to your system. So I'm walking along this mountain trail, and I know that my derivative of height with respect to time is always positive. What does that tell you about the trail?
Your elevation is increasing?
Yeah, it means you're always going up. It means you're always crossing the level curves, going from low to high. Okay, so let's go back to this graphing program. Sorry for switching back and forth. I don't know, maybe it's more interesting for you guys if I keep switching back and forth, keeps you awake, right? Here was, again, the picture of this modified system where we added the friction component. And we're comparing that to the level curves. And here was the three-dimensional graph of the surface. So now imagine you're walking on a path, and that path is always traveling on those level curves, and the height, your height is always increasing. You see what's going to happen if you're crossing these level curves in a way that your height's always increasing? Eventually, you're going to spiral up to the top of one of these mountaintops. Okay? So knowing where those level curves are really, again, tells you what the whole picture is. If I forget about the vector field, if I never solve for that vector field, knowing that the centers here are peaks, and knowing that solutions to this new system always cross level curves going in the uphill direction, you can kind of tell eventually you're going to have to spiral uphill around this mountaintop and go to that center. So it just gives you a little bit more information. The fact that dHdt was always positive tells you we're always crossing from low to high on this h function, and you're always crossing those level curves. Another thing this tells you is that things are trapped. Think about this level curve. You see where my pointer is. This sort of elliptical level curve out here. Once you cross that elliptical level curve, you can never get out, right? Because we're always going from low to high. So once you cross a contour line, if you can't get back down, because then you have to go from high to low, right? So another thing you can use this picture for is to trap trajectories. As soon as you cross a closed contour line that makes a loop, you can't get out. And that's really powerful qualitative information. If you have some system, you don't know much about that system, but you know you have this function, and your trajectories always cross level curves from low to high for that function, that tells you once you're trapped in a particular region, you stay trapped forever, for all time. So you probably have some spiral sink or source or something. Spiral sink or just a regular sink in there. Okay. So again, you know, knowing these texts gives you a lot of information. These systems, this is called, I'll go back yet again to my iPad screen. I'm going to move your window over, good. These systems are called dissipative systems. Right? Because there's some energy that's constantly being lost, it's dissipating, like in this case, the sum of potential energy and kinetic energy is a dissipative system. In a dissipative system, what you see is that dHdt is always greater than or equal to 0, or dHdt is always less than or equal to 0, one or the other, right? But not both, right? And that tells you that either you're always traveling from low regions to high regions. Every time you cross a contour line, you never cross back, right? Or you're going from high regions to low regions. Just flip the picture upside down in the second scenario, okay? So both those situations are exactly the same. It'll look like you're just constantly crossing contour lines. And you'll never be tangent to contour lines unless it actually equals 0. When it equals 0, you'll be tangent to the contour lines. Where it's greater than 0, you'll be crossing the contour lines. So that greater than or equal to 0 does allow you to be tangent to the contour lines. That's only happening at those places where you see equality. Right? For fancy reasons, this new function h, we don't call it h anymore because it's not Hamiltonian anymore. It's not a Hamiltonian function. So instead of h, we use the letter L. Really, so really I should be saying dl dt is always greater than or equal to 0, or dl dt is always less than or equal to 0. And that stands for a Russian mathematician whose last name was Lyapunov. And so this function, we don't call it a Hamiltonian function anymore. We call it a Lyapunov function. And sometimes these are called dissipative systems. Sometimes they're called Lyapunov systems. Again, this is all in the book. This is section 5.4. And they start out exactly the way I've started out going through this pendulum. I see I'm out of time right now. So let me just say just a tiny bit where they go from this. They give one more example after they do this. The tune mass damper, it's another kind of oscillation. I'm not going to go through that example because it's much more involved. There's a tiny bit at the end of this chapter on other places these kinds of systems might arise, called gradient systems. I'll pick up there next time. So we'll finish this chapter next time. I'll pick up with gradient systems. Again, there's no web work problems. So for homework, I want you to make sure you've, first of all, read this chapter. Read section 5.4. And if you haven't done it, you should read the Hamiltonian chapter 2 on 5.3. Should look very familiar. It's all stuff we've done. You should do the 5.3 problems if you haven't done them already. And then in section 5.4, I would try a couple of those problems. So some good ones were number one's a very reasonable problem. There's not that many that I think are good problems. Let me just look real quick. I looked at these earlier, then I stupidly didn't write them down which ones I thought you should do. 3 is good. 5, 4 through 11 is just more stuff about the undamped pendulum. I don't think you need to do those. And 13 is about gradient systems, which we'll do next time. So when you get to 13 and the later problems, I'll assign those next time. So just start with 1 and 3 for now. Make sure you do the 5.3 problems, and then just try problems 1 and 3 from 5.4. That's it. Last questions? Last minute questions? Sorry, I know that was a little bit grueling. I think I just talked in a mile a minute for the last hour and 20 minutes. You good? Okay.
Thank
See
you.
you next time.
Thank you.
Sure. Bye.
Thank you, Professor.